or 25 minutes, I will be discussing about some methods for doing some polarization difference spectroscopy on micron scales under magnetic fields, which we have been developing in the last few years. And I will also show some preliminary data because this is work in progress. Science still has to be done quite a bit. The methods are mostly ready. Okay, so this is the group at the moment. We welcome two new postdocs as well within this month. We work on two-dimensional quasi-particles such as excitons, trions, and so on. In two-dimensional materials, layered materials in magnetic fields where we study all these effects such as Zeeman splitting, valley coherence and polarization, Landau quantization, diamagnetic shifts, and so on. If you are curious to learn about this field, I invite you to read this perspective, which I wrote during COVID times, by keeping interests of students in mind. So you are welcome to take a look. We develop all these optical spectroscopy methods in our lab, as well as magneto-optical spectroscopy methods. I will tell a bit about these. And the ongoing projects involve these excitons, trions, many-body physics under carrier densities, or 2D excitons and magnetisms in this two-dimensional magnetic materials and so on. So initially, I will introduce to polarization difference spectroscopy and then continue for these three methods. The first one involves out-of-plane magnetic fields, second one is in-plane magnetic fields, third one is no magnetic fields. Differential spectroscopy is very interesting. Here we perturb the dielectric function of a material periodically. For example, periodically shining laser or applying strain wavelength or changing the polarization periodically. It's interesting because it gives an idea of very weak resonances in the crystals, or very weak effects in the crystals can be measured with high signal to noise ratio. Because there are some resonances, and when we detect the signal at the frequency of this perturbation or this modulation, we measure the difference between two different states, say two different polarization states in this talk. And this difference is maximum around certain points in the Brillouin zone, which are connected with some resonances, suppose. And even if these are weak resonances, we will have strong signal around them. There are sharp derivative-like line shapes because these are difference methods. There is no DC background, therefore signal to noise ratio is high. For example, if we pump a system with a laser, say CW laser, periodically, and probe the system using a broadband light, then what we can do is we can measure the response of this reflectance spectrum of the system in the presence of pump and in the absence of pump and take a difference. So essentially we are measuring the difference live, and it is very sensitive. We can take an example of a quantum well where a gallium arsenide layer is sandwiched between aluminum gallium arsenide barriers. There are these two sub-bands of transitions which are visible in absorption. Whereas if you look at photoreflectance, which is this spectroscopy, we measure also the excited states of excitons. In fact, I was sitting with Sandeep yesterday, and we also found that we are even able to see excited state of an exciton of the second sub-band, which is very interesting. We never knew that we were seeing it there. So this spectroscopy is sensitive towards weak features or excited states of excitons, for example. Similarly, we can modulate the polarization between two states of either linearly polarized light or circularly polarized light and measure various effects as a change in the two orthogonal states. For example, if we talk of ellipsometry, we shine light on the sample, modulate it, and measure the change between the S and P polarized components once it reflects, and this change has a lot of information encoded in it, such as dielectric function of the material or the thickness of the material. Similarly, magneto-optical Kerr effect, which deals with change of right and left circular polarization. Schaefer-Hubert effect, again linear polarization. I will discuss these. Similarly, Faraday and Vogt, I will discuss these in this talk. Take an example of Bock, magneto-optical Kerr effect, where incident light, if it's linearly polarized, reflects off from the surface of the material under magnetic field, we get something like an elliptically polarized light. So it has rotation as well as ellipticity. This can be written as a complex function, a complex rotation. Essentially, there is a rotation and an ellipticity. And if we look at this rotated and elliptically polarized light, there is this angle which is rotation and this angle is ellipticity. Phi k and eta k. This is phi and this is eta. So essentially, this is what we measure in such methods. An example again of a quantum well is shown here, where if in absorption we see a few resonances in magnetic field, in Moog we see maybe 15 resonances. So it's very sensitive. That is the idea. Again, unpublished with Sandeep. But I keep learning from all this data because there are too many gems hidden within all these resonances, these weak resonances. A typical Moog setup is here, where there is a photoelastic modulator which modulates the state of polarization. Light reflects from a mirror, then from the sample, and goes to analyzer and a detector, which is a PMT in this case. We can measure both Kerr rotation and Kerr ellipticity using such a setup by using lock-in amplifiers, where you measure signal at the frequency of modulation and twice the frequency modulation and the DC signal. And using these three signals, we can find Kerr rotation and Kerr ellipticity. There are these two things, delta and tensor, called ellipsometry parameters of the mirror, which we have to measure separately, which we do separately, and we find Kerr rotation and Kerr ellipticity. So using these, for example, again in a quantum well, wherever there are sharp resonances, I told you that the difference in this right and left circular absorption is large, and then you get some Kerr rotation or Kerr ellipticity. This is Kerr rotation here. And if there is no Zeeman splitting, this will be 0. Because there is Zeeman splitting, there is some phase difference now between right and left circular polarization. So there is some rotation from which one can find G factors. In fact, one can find very low Zeeman splitting, such as on micro electron volt level, using these sensitive methods. That's the idea. Similarly, we made a recent discovery in 2025, where in fact we found a very weak state called an excited state of a trion, which does not appear in any reflectance of this quantum well. So this work was led by Saurabh, sitting somewhere in the audience. And this excited state of a trion should appear somewhere there, not visible. Apply magnetic field, it should gain strength, but still not visible. It should be somewhere there. But as soon as we measure Kerr rotation, a beautiful signature appears. We measure all its properties and we find that this is a trion. So this was the discovery which happened only due to Kerr effect, or the sensitivity of this technique. We can do much more. I talked about Kerr effect, but we can do Faraday effect by applying again out of plane magnetic field, which is in transmission. Kerr effect is in reflection, Faraday is transmission. We can apply fields in the plane, and we can do Vogt effect, which is in transmission, Schoffer-Hubert, which is again in reflection. Again, everything is the same, direction of field is different, and we are measuring change in the state of polarization. That's it. And using all of these, we can measure lots of things about spin polarized or magnetic moment polarized band structure of the materials non-destructively. We can measure small exciton G factors or small signatures with high precision and high accuracy in two-dimensional semiconductors and two-dimensional magnetic materials as well. Similarly, we can do ellipsometry either in transmission or reflection, as I talked about. And this is useful for measuring complex refractive index and thicknesses. Now, there are many problems with these methods. The problem is that when we do modulation, we have to come wavelength by wavelength. So at each wavelength, we are measuring our signal, stopping there for 2 minutes to acquire sufficient signal to noise ratio, a good signal to noise ratio, and then move to the next wavelength. And if once you do this, suppose there are 100 data points, 200 minutes for 100 data points is like 3 hours, which is what I was doing all the time. And this is how the world does all of this before this work. The problem is we can't be too slow for two-dimensional materials because the light spot is very small, one. Sample spot is also very small because once you encapsulate samples between HPN, there are very little regions of the material where you are allowed to do spectroscopy. And in the presence of magnetic field, things are moving a bit when they are also at low temperature. So even if they move like 50 nanometers, we notice that we lose signals, which means that we have probably 3 to 4 minutes available for measuring these things. So we have to come down from many hours to 3 to 4 minutes. So we have to invent something new. So this is our goal. So we have to develop all of these on micron scale. We have to do spectroscopy. We do not have to modulate if possible and gain spectral acquisition speed. So this is where I come to our work of Faraday rotation, which I developed during postdoc and also. So this is how I had more hair during postdoc. That's why Faraday rotation worked. Now I have a student who has a lot of hair, and Kerr rotation is working these days, led by Gautam. So let me come to the setups and the results. Essentially, we have gotten rid of photoelastic modulator. These are stationary components now, a polarizer, some beam displacer. Essentially, this beam displacer, what it does is, if you have a 45-degree polarized light, there is S and P component, so this splits these two components in space. So you have now two orthogonal components which are available for you to measure. And by doing some math of this system, which is not that easy as it looks, one can find Faraday rotation. For example, write Jones matrices of all these components, multiply these Jones matrices as the setup allows or as the setup is built, and finally find intensities which are beam displacer split, and do some things with the intensities, like take difference and take sum and do something with them to find if one can find Faraday rotation or not. So these two intensities, IH and IV, are the horizontal and vertical polarized components coming out of beam displacer, which we are putting on the spectrometer. Essentially now, if we are using a CCD, we are putting these two polarized components on the spectrometer, so in one shot we have full spectrum. And the thing is, take one spectrum by up direction of magnetic field or one direction of magnetic field, take another spectrum by reversing the magnetic field. These have some complicated equations, but once you subtract these, it simplifies. What is remaining is tan psi, and tan psi can be measured separately of this mirror which is there. And this is how the setup works. This is Faraday rotation. Measure this, find Faraday rotation. How do we know this setup is working fine? Well, we use another method to test the setup. First, cross two polarizers, no light coming out. Then introduce a rotation by hand by putting a half wave plate which rotates the polarization of light, and cross it again. So we know how much rotation we have introduced. The same rotation we measure with our setup, and everything falls on the top of each other, which means the setup is accurately working. At the same time, we can measure how precisely we can measure things. For example, if we measure RMS noise. Now, this orange shaded region is the RMS noise, which is typical in modulation spectroscopy setups, which is obtained after many hours of measurement. However, after 3 or 4 minutes, we notice that this RMS noise of our setup is similar. Therefore, we start to win already after 3 or 4 minutes. First results of this using this setup appeared on molybdenum diselenide, for example. Measure Faraday rotation around the excitonic lines, and we find that you fit these and find G factors of exciton and trion. Well, they agree with literature. At the same time, find Veddet constants, which means Faraday rotation per unit magnetic field per unit thickness of the material. This is a number which is very important for industrial applications for polarization, rotation, and so on, polarization rotators. And we find that in such materials, the Veddet constants are of the order of 10⁻⁷, which are largest ever found to the best of our knowledge in any material. So basically, these materials have potential for future generation of ultra-thin polarization rotators, which are used for all optical integrated circuits. Anyway, this is just one result, but this talk is more about techniques than science. Following the same principles, we build Moog spectroscopy setup. Again, a polarizer, beam splitter, reflect light, falls on the sample, comes back, and beam displacer. Now this becomes complicated because there is a beam splitter here, there is a mirror here, and everything has its own tan psi and delta. So we have to measure them separately. Well, do the math. Again, two polarizations, 0 degree, 90 degree, two measurements, take a difference, solve these for phi k, which is curve rotation, and we find that there is this tan psi and delta of beam splitter and the mirror. This comes into picture. Okay, to test that this setup works, well, this setup works first of all. Now to test, what we do is replace the sample with a quarter wave plate and mirror and introduce a rotation with hand. And then we know that if by doing the math again, if we rotate quarter wave plate by theta, the expected rotation is 2 theta. This is exactly what we measure. So this dashed line is expectation, solid lines are measured and they fall on the top of each other. Of course, there are small deviations which are because the quarter wave plate is not perfect quarter wave plate. There are deviations from 0.25 in quarter wave plate itself. Okay, so the setup should work. In fact, it works if we measure curve rotation of a tungsten disulfide monolayer. It looks very nice. Measure G factor minus 4.5. Again, agrees with literature. All of this is very nice. So MOOC spectroscopy setup is working, and we have to publish this soon. Now we come to works which are led by Abhishek and Bhumika. Bhumika is sitting somewhere in the audience. These are works for in-plane field, where either we reflect light, Schoffert-Hubert, or transmit light, Vogt effect. The names are different, but measurement scheme is the same. It becomes complicated, you will see, because of some geometries which we have to achieve. For example, these effects are very nice, first of all, because when we apply magnetic field in the plane of the system, the materials, some direction where magnetic field is applied offers slightly different refractive index compared to the other direction, so material becomes birefringent. Therefore, one can measure these in-plane things by the birefringence of material in the presence of magnetic field or in the presence of magnetism, which means the 2D magnets which have in-plane magnetic fields, in-plane magnetizations, or even if they are ferromagnetic or antiferromagnetic, both work. Essentially, if we are looking for some smoking gun to understand if there is an antiferromagnetism in the material, it's a very difficult task to achieve because the net magnetization is 0, but these effects work. That's the reason we are building these. So all these materials which have in-plane magnetizations will be our test samples for our future. Okay, so I call these setups as 1, 2, 3, and 4, and we go through 4 of these quickly. Similar things, Vogt rotation, again beam displacer with some components, make 2 measurements, and check if the setup works by replacing the sample with a half wave plate by introducing a rotation yourself. Well, it works. I will just flash all 4 setups work essentially. Again, Vogt ellipticity, you need an extra quarter wave plate. The formula is different for finding ellipticity. Again, replace sample with a quarter wave plate and a half wave plate, and we should be able to measure ellipticity, and it works. Expected and measured are the same. In Schoffert-Hubert rotation, reflect light, formula becomes a bit complicated because of beam splitter, and then replace the sample with a quarter wave plate and a mirror as earlier, works. Similarly, for ellipticity there is an extra quarter wave plate, formula is much more complicated now with tan psi and delta of this beam splitter in the picture, but more or less it works. And this is our first data which we obtained just last week. I mean, there will be more, but at low angles it seems to work well. Where in the test we have to replace now the sample with 2 quarter wave plates where one of them will rotate, and then the expectation is eta by 2, and this is what we measure. Okay, now to test these, one of these, I will show just one of these, which is Schoffert-Hubert rotation setup, which is already very complicated, but I have to check if this works. We test these on 2 2D materials. One is tungsten disulfide, which is isotropic. Now, once something is isotropic, the linear polarized birefringence does not exist within the plane, so there should be no rotation. Similarly, if I pick something such as ERPS4, which has in plane an isotropy, this should have some rotation because this is linearly birefringent already. And let's check if there is something. Well, tungsten disulfide, no rotation as expected. In fact, we change the direction of the sample, we rotate the orientation of the sample with respect to polarized light, and we find that no rotation whatsoever at any angle. But for CRPS4, beautiful rotation line, and we change the angle of the incident light with respect to the a-axis or one of the axes, and we find that this rotation curve changes. So the dichroism is direction dependent in the plane of the material, which is expected because in literature also around this 2 electron volt there is a resonance which shows dichroism. A weak resonance, but appears very strongly in our method because these are very sensitive methods. Okay, so this works. Next we have to do all of this in magnetic fields because all of this so far was in the absence of magnetic field for testing, but now we have built the setups in magnetic field, and this is what is going to give us some more science for in-plane magnetism. Finally, Vinod, sitting somewhere in the audience, is leading in development of spectroscopic ellipsometry on micron scales. Now this is interesting because this ellipsometry is useful for measurement of refractive indices as well as thicknesses of thin films like two-dimensional materials which are very thin. We have to measure some quantities called tensai and delta. In literature they are just called like that, but what it means is there is some polarized light which is shining on the surface of the material. It has S and P components. The ratio of the reflected S and P amplitudes is related to tensai, and the phase difference which appear is related to delta. Now both of these have to be measured. Again, this is all measured using some compensators, which is say a photoelastic modulator which is modulating the state of polarization of light, or some rotating polarizers and so on, wavelength by wavelength. So these are very slow, but we have to make it fast. Also, if you want to buy such a system, it's very expensive, like more than 3 crores. So why not build it on our own in a cost-effective manner? Well, we have built it maybe within 25 lakhs, so which is much more cheaper compared to this. And we also are able to do microscopy. We are also able to do spectroscopy in one shot using the methods, which we develop. Again, similar things, some components, don't go into details. This looks complicated, it's not really. But these are just polarizers and quarter wave plates and half wave plates put at some specific angles such as 22.5 degrees here. Then there is a Wollaston prism, again 2 polarizations, which we are measuring using 2 small spectrometers, pocket spectrometers, which are cheap. Find tensai using this arrangement, introduce an extra quarter wave plate, find delta. That's it. And we can test. Now we find, for example, suppose we have these 2 test samples like a piece of silicon wafer. Now we know that there is always an oxide layer on the piece of silicon wafer, and this oxide layer is only a few nanometers thick. We measure their tensai and delta, and we fit these and find that this thickness is 4 nanometers within 0.1 nanometers. So that is the precision as well as accuracy of this setup. Well, accuracy I am not so sure, but this agrees very well with literature. But take a tungsten disulfide flake. This one is a thick flake. Find tensai and delta, model this and find refractive indices. They agree excellently with literature. So we have quite a bit of confidence that this setup works as well. So all in all of our setups, the spot size is of the order of 1 micron. We have 1 short spectrum, and all of these are compatible with low temperatures and magnetic fields. In fact, the next step is to do magneto-ellipsometry. Okay, so here I would like to conclude differential effect spectroscopy is very sensitive, where we can develop all these 4 methods here with in-plane and out-of-plane fields, and also ellipsometry. And we have some preliminary data suggesting that everything works. I have one more announcement. Recently, due to National Quantum Mission, we had promised a company, and now we have registered this company. It's called Yantram Instruments Private Limited. The goal of the company is to get rid of imports as much as possible, because we spend lots of time and lots of money importing stuff, high precision equipment. So we have started by building our own magnets up to 1.8 Tesla. These are air-cooled magnets. Magnetic field is 1.8 Tesla at 20 mm pole gap. Also, there are some bores in the magnets where we can put objective lenses and do spectroscopy. On a micron scale, there are some vector magnets and all. Abhishek and Bhumika have been designing all of this. We presented some of this at the Quantum Conclave at IIT Bombay very recently. This is a magnet lying here. This is a 2D transfer system which we also promised to give away at reasonable prices. We also build optomechanics, some achromatic doublets, some mirrors using our partners. So we have this cost-effective company coming up. I'm happy to talk more about this if you are interested. I thank everyone from ICER Pune, students and some faculty and some postdocs, and from TIFR, Sandeep is sitting here. Also others who have participated in this works, and I thank you for your attention. Also this funding.
Thank you very much for the wonderful talk and the update on your instrument development. So I expect several questions. Very nice work. I'm very impressed. One question about when you are looking at linear polarization anisotropies in these samples, which already have a linear polarization, this sample.
Yes.
Then when you apply the magnetic field, how are you going to distinguish between the effect of the magnetic field and something which is already...
Wonderful question. We don't know yet. If the anisotropy is too large, we don't know yet. But thank you for being impressed. I wanted to hear this from my PhD supervisor always. Today I heard.
So like when you actually work with real samples,
Yeah.
so like all the analysis relies on Joule waves, right?
Yes.
But there can be some depolarization effects which will be important also in the sense,
Depolarizations. Then we have to do Stokes polarimetry.
or like Muller matrices.
Correct.
Much more common.
Yeah, so far we have not done that.
That's probably not important.
Probably not in these samples so far, but when we do suppose luminescence, then you know, you shine linearly polarized light, you expect linear out, but there is depolarization component, then it becomes a challenge to find G factors. In transmission, we do not see any depolarizations. Perfectly polarized whatsoever. That's what we have seen in all 2D materials, or in reflection also.
Yeah, I have a question about transfer state. Like,
Sorry again?
Question about transfer state. Is it ready to sell or like still you are?
2D transfer setup. Yeah, it's ready to sell.
So okay, then I can talk to you.
Sure. Sure. In fact, we also provide a spectrometer, a small spectrometer for live spectroscopy, and we also provide PL imaging. So essentially, you can check live PL, and then you can find monolayers directly in the PL image. All of these things are included.
Any other question?
Yeah, I have a question. So, thanks Ashley for a very nice talk. Probably discuss details with you later. I had a question about this NATCOM work. Yeah. So, you created this super sensitive setup, but then you ended up measuring a quantity which is huge. Right? So, you could have done it with a less sensitive system as well. Right? So, firstly, what was the point?
The point is that to measure G factors, for example, for that quantity which was huge, which looks huge here, using just magnetoreflectance or magnetoluminescence, you need many Teslas of magnetic field. Here we are able to do it at 0.05 Tesla, for example. So a factor of 30 or 40 low magnetic field. So you take to your electromagnet and do it.
I see. That was that point.
Sensitivity helps. Also, valley polarizations of 0.05% we measure. Very small.
Okay, fine.
Okay, so let's thank the speaker again.
Thank you very much.
So our next speaker is